Okay. Hi. My name is Josh Fischer. I am an engineer with 1904 Labs in St. Louis, Missouri. Over the past few years, I've dealt with moving a lot of data. I can't center a div to save my life, but some of the problems I've come across is moving requests across a network that could be up to 900,000 lines of JSON, or something that has to process 60,000 transactions per second with a 20-second SLA. In the last year, I was working on that project it was high velocity transactions. Had to handle a lot of load, and I had to respond quickly from anywhere in the world. And this kind of got me into this whole streaming framework architecture. So in this talk, we're going to talk about what actually Apache Heron is. My experience of bringing in a component into the Heron system, and then actually building a Heron workstation file. And I'm going to finish up with some thoughts about my whole process of trying to integrate Bazel and understand open source projects all within a certain time period and produce something workable for a client. So Heron, by text definition, is a fault-tolerant distributed stream processing system. It is a successor to Apache Storm, or from Apache Storm. It was developed in-house at Twitter. It was there was a point in time when Twitter had their entire infrastructure running on Storm, and they experienced some issues with running systems when high load would hit, and they found that when Super Bowls would happen or high traction events would happen, that eventually Storm would drop transactions, and this led to inconsistent metric reporting, inconsistent ad impressions, and caused quite a lot of issues for their clients. So the team got together and they decided to build the successor to this, which is compatible with all of Storm's topologies. So I spent some time looking into, trying to find some, cool stuff to talk about, and I reached out to the people at Twitter and I said, what was the reason for the Heron name? Apparently it's a thing at Twitter to name all their projects after birds. I had no idea. And I said, well, what was the significance of Heron? I mean, there's got to be something, because I figured out these birds can be 5 foot tall with a 7.5 foot wingspan. So I'm like, it's got to be related. And the answer I got was, I like long-legged birds, and something like crane was already taken. So this is what we got. So use cases for Heron or any streaming system, specifically Heron in this case will be real-time ETL. Twitter uses it for spam detection and real-time trends. Whenever there are high-velocity events going on. If you wanted to, you could do real-time business intelligence. There's also some research going on right now with real-time machine learning. I've sat into a couple of the talks. It's not really my thing, but I know it's in progress. I don't know where they stand right now. And I've said real-time enough, so if it has a real-time need, most likely Heron is what you can use. So some simple terminology to go over before we get into what the system is and how it works. When you load jobs into Heron, you run topologies. Topologies are nothing but DAGs. DAGs is an abbreviation for directed acyclic graph, which is a really fancy word for circles with lines pointing to other circles. It's just a way to show how data can logically flow through a topology. Spouts will be your source for data from the outside world. So spouts can read from MySQL tables, Cassandra tables, Apache Kafka queues, Pulsar queues, and so forth. And then bolts will be doing all the downstream processing and making decisions based on the data that's passed through the topology. And then to connect those spouts and bolts will be edges, which will be your streams of data, which is wrapped by a data tuple object. So this is an example of a simple DAG. Very simple. So in this case, you got one spout, 4 bolts. Spout 1 can then emit data to B1 and B2. B1 can then emit data to B1, B3, and then B2 goes straight to B4. They actually have some generated topologies that'll run across 1,000 nodes that'll have hundreds and hundreds of these. This is just very simple for you to kind of digest. And if you get into what actually makes up a topology, this is kind of the low-level view in a way. A high-level, low-level view of what a topology is. Heron is nothing but a bunch of running topologies or a bunch of Heron jobs. And every topology is going to have its own topology master. And then down below, you'll see these data containers, which these dotted lines. Within those, you'll see a stream manager, a metrics manager, and these boxes, I1 through I4. Stream manager is used to, for inter-container communication and the register itself with the topology master. Metrics manager is used for debugging purposes for developers, and then I1s through I4s are those individual instances of the spouts and bolts that you've declared in your topologies. And then, I'm not a fan of this image, but this is the best I could find in the short time I had to do this. There's a zookeeper cluster that is shared between a topology, a Heron cluster, not a topology. So you can have 1,000 Heron topologies running, all running off one zookeeper cluster. And within that zookeeper cluster, you'll keep logical plan, which is the DAG, your physical plan, which can be your IP addresses and your ports, and then a current execution state of the topologies that are running. So the tech composition is mainly Java. Then it has, probably behind that is C++, then Python. So Java would be those Heron instances, and this is not exclusive, this is limited to, this is just a short list I put together. So those I1s through I4s, those are a JVM process. C++ will be your topology master stream manager. Python will be your CLI, and then your UI, and then we have shell to kind of smooth out the rocks in between. So an issue we had or issue they had, and then I came across as I started working on this project, is that, how do you handle all these different languages with one tool? And Bazel was what stepped up and did the job for us. It's also possible to write topologies in Java, C++, and Python, but no matter what type of topology you write, it's going to be managed by a JVM process for now. There is something in the roadmap to take that away, but that's what it is for now. So when the time came to design Heron, the team got together and they thought about, did we want to write a scheduler? Did we want to write a state management? What about metrics? And with the time they had allotted to get this project done, they decided that it was best to focus on what Heron was going to do, and that was stream data. So Heron has implementations for running on top of Kubernetes, Apache Mesos. It runs in production at Twitter right now on Apache Aurora. State management is Zookeeper, and then you can plug in metric syncs such as Prometheus and Grafana, and then visualize those with Prometheus and Grafana, Prometheus and Graphite, and then visualize those with Grafana. So, I had this project I was working on, had a high need for real-time transactions, like within 20 milliseconds, and there was this homegrown streaming framework that had kind of gone out of control, hard to manage. It was, as developers left, there was patches put on top of code that was already there, and it was your typical project that had siloed teams working on stuff. So we came in and we had to design a new system from scratch, but a requirement we had is that topologies had to be designed in a way that they weren't written in code. Fun, right? So out of the gate at that point in time, Apache Storm had something called Flux, which allowed for a YAML spec to define a topology and how data can flow through those topologies. And in my own selfish way, we decided to go with Storm for the project because it had Flux, but I decided to go off on my own and write Eco so that when Storm didn't work, we could bring Eco up and run all of our existing topologies in Flux and bring them over into Eco, and it would just work. So right away, your Apache Heron project is a monolith repo. So you'll have a bunch of top-level directories. Heron's going to be where most of the code is. And then for more of the third party or the external code, you'll have your Storm compatibility, which offers all of your Storm files. And then you'll have Eco, which is all your Eco files. And you'll have Docker, and then you'll have scripts for building the project and so forth. So while bringing this in, Apache Heron has 3 outputs right now. It has an install script, it has a Heron Maven artifact, and has a Storm compatibility artifact. And the challenge I had while drinking from the fire hose, trying to understand how Heron worked and how Bazel worked, was trying to include Eco into the Storm compatibility artifact, even though Eco was dependent on Storm compatibility, which caused that cyclical recursion, and it caused a lot of issues. So the way I had to structure Eco is we have a couple packages. Well, we have a top-level package, and then within each package we have different blocked off places of functionality, and each one of those is going to be a Java library that are all rolled up into a final output, which includes the top-level Eco class in the final library. So if you see here, we have dependencies for eco, and this is a very abbreviated list, but I got snake YAML, and then I have this link here to storm compatibility, never link. This is the key to causing Bazel not to blow up when you try to include a dependency that's dependent on another dependency. And then within each one of these packages, we'll have a Java library specific to that package, which creates an artifact, which here at the bottom, you'll see our final output is eco Java, which references that top-level eco file and then references all of the other dependent libraries that were left out for brevity. There wasn't enough room to show on the slide. So then over on storm compatibility, I had to add a separate library that was a complete copy of what the Java library was, but I had to add that never link flag equal to 1 so that it wouldn't cause that issue when I tried to build eco. But then you'll see down below we have this unshaded Java binary that includes eco, which is then uploaded into Maven with this jar jar binary rule. It does some moving a class pass and makes a production-ready build. So I got eco figured out, and then it was time to actually build the whole project and bring this into a whole. And we have we reuse a lot of package tars. And the script I'm going to focus on is this Bazel build --config equals Darwin scripts / packages bin packages. Right now we support Heron for CentOS, Ubuntu, and Darwin. Building per platform is fairly simple. You just pass a config flag, and then we just know how to take care of how executables be placed in your path. Okay. Can you guys cut over to my computer? Oh, that's not good. There we go. So what I want to show you is we have a install script that is generated. And actually, I also upgraded Bazel about a week ago, and it broke my entire build, so that's another thing to work through. So I'm just going to show you what the artifact is. So basically, you run this Heron install script, and it's going to install this stuff in your path. It's going to uncompress a tar.gz file, or a couple of them, print out some versions and some generated times that are from when the build was completed, and then you have Heron in your path for a workstation. Can you cut back over to the slides, please? So the output of that comes from this. So we have a file group that references a self-extract binary, which goes to this package tar, which loops around to this other package tar, drops down here to this other package tar, squiggles over to another one, and then loops around up here to a macro that references some Python and C++ files. Fair? So stepping in, so what I plan to do is I'm going to take that command, I'm going to roll back all the way down to some source code. I'm going to step through the tar packages, or the package tars, just so you can see how we can hook up one path of them. But then I'm going to go in depth into this custom rule that does all the work to generate in the script. So our bin packages target is just a file group that references this Heron install script, which is output from this custom rule. And I'll come back to an implementation of this, but for right now, we have a couple attributes. We have the name, which will be the output file, flatten resources, which is, it takes a package tar, which will, it'll basically pull the files out and put them in an expected directory structure. And then we have the launcher script, which actually does all the work, which moves stuff around, installs stuff, checks Java, checks Python, and so forth. So I'm going to kind of branch off and come back to this, but I'm going to step down to the package tar path for now. So this package tar references a Heron tar.gz, and it has some sources which are a release.yaml. It's just your, you saw it up on the console. It was when the build was generated, what server it's at, and so forth. And then it's got some dependencies, which are all tar.gz files. So I'm going to step into the Heron disk, which is a package tar, which cuts some sources that it packages up in the disk folder from another tar.gz file, which will go through, which is dependent on other tar.gz files, as well as that release.yaml. And then finally, you get this last package tar, which is this is only one path. Gets its sources from a macro, which references a bunch of Python and C++ targets. So if you step back, we have this self-extract binary, and we just went through that whole mind-numbing thing of going through all the package tars. Now let's step into what the launcher is. The launcher is an output from a gen rule, and it takes some sources, which is template bin, template underscore bin, bin underscore common, and then that handy generated release file, which is a release.yaml. And what this gen rule does is it cats out all of the contents of those files into some bash variables and then echoes them out into this final output, which is launcher underscore bin. In case I didn't say, bin underscore common will do some environment checks for Java, Python, so forth, and then launcher bin or template bin does all the work. So if we get into the definition of the rule, or the declaration of the rule, we have some attributes. The only ones we're going to worry about is the launcher and the flatten resources. So specifically here, if you look at flatten resources, it's going to go through this is the definition of the rule, by the way. It's going to go through and it's going to copy all these files into a temp directory. And then finally in the second action, or in this first action, it's going to output all these files after it goes through, does a bunch of bash, and it's going to output this into a zip artifact target, or zip underscore artifact output, which can then be referenced from another action, which then cats all those contents out of the launcher script and then all the binary from that targz file into one self-extractable install script. All right. So I took some time and I was trying to think of something to kind of come up with, show something really cool with Bazel and Heron, and I found out about the whole action graph and the dependency graph you can generate with Bazel. And so this is a very simple one I generated. I found this online. I copy and pasted it into a tool which I think is called Visual Graph Wiz. And I figured I'm going to do this with Heron. This is what I got. And this is actually a screenshot of the actual image because the image was so big I couldn't load it into Google Slides. So I found a way to generate an SVG, and the image was so big there was no way I could have shown you anything of value. So I decided to focus in on just one target. And you see all those that dark line, that's all several lines crossing over each other, but it's a very complex system. So overall, I took the time to transition from this whole, Apache, Heron, Bazel way of thinking from, a traditional Maven mindset. I think one of the first things I came up with was like, where's my M2 directory? I couldn't find it. And I've come to really appreciate what Bazel has to offer. I like the notion of hermetic builds. I found out that I don't think Heron is actually very hermetic this week. But I found some ways to improve that while sitting here. I like that you can build multiple languages with one tool. And then I love remote caching. I think cutting a release for Heron will take 45 minutes to an hour. Being able to cut that down to 5 minutes is pretty cool because, I'm the king of messing something up. I mistype something and blow up the whole project. It's terrible. Some of the issues I've found so far is this Bazel version compatibility. Sometimes, and maybe this is just my not knowledge of the tool, enough, is that, I'll upgrade Bazel and it totally break my entire build. And sometimes I can work through it, sometimes I can't. And as a developer, I'm really lazy. I love that I can search for an answer and get 500 results. Right now, I think community use is a little thin. But I think over the years, as people start to understand how great this tool is, it'll pick up a lot over the years. So we went through what the process was of building Heron. We went through some experience I had with working with Eco and actually creating this whole entire build install script. And then we ended up here. So I really appreciate your time. Thank you so much.